A razor blade cannot slide between the stones of an ancient Inca wall. This is the legacy of builders whose precision defies all modern explanation. You are about to discover the secrets behind a global phenomenon of inexplicably accurate stonework, from the Andes to the temples of Egypt. This journey will reveal how our ancestors accomplished feats that challenge everything we think we know about their tools and knowledge. How did cultures across the world, separated by oceans and millennia, achieve such perfection without any power tools? What forgotten methods allowed them to cut and fit granite with a level of accuracy we would struggle to replicate today? What does this ancient mastery tell you about the true potential of human ingenuity? A single sheet of paper cannot pass through the joints in that Inca wall. This is the standard we are talking about when we describe unexplained accuracy. It is not merely a poetic phrase for something being well built. It is a technical reality, a measurable phenomenon that continues to baffle engineers and stonemasons today. This precision refers to stone blocks cut and fitted together with tolerances of less than a single millimeter. Think about the width of a credit card or the edge of a razor blade. That is the minuscule gap, or more accurately the lack of one, found between stones weighing many tons. These are not simple, square blocks. They are complex polygonal shapes with multiple contact surfaces, each one perfectly flat and each edge perfectly straight, locking together in a three-dimensional puzzle. Archaeologist Jean-Pierre Protzen spent years studying these walls and concluded that the builders possessed a method for creating these incredibly precise, irregular shapes that we simply do not comprehend. They achieved this without any power tools, without standardized measurement systems like the metric or imperial foot, and often working with materials like granite and basalt, some of the hardest stones on the planet. The implications are staggering. If they did not have the technology we assume is necessary, then what alternative knowledge did they possess? This foundational mystery of surface flatness, edge straightness, and complex interlocking forms is the very heart of the enigma, a global signature of a lost art. This same impossible precision is echoed across the world, in cultures that could never have met. Far from the Andes, the towering temples of Angkor Wat rise from the Cambodian jungle, their sandstone blocks joined with seams just as ghostly thin. On the other side of the globe, the Cyclopean walls of Sacsayhuaman in Peru lock together in a zigzag pattern of stones so enormous and so perfectly fitted that the entire structure has withstood centuries of earthquakes. From Mesoamerica to the Mediterranean, the signature is eerily the same. How could civilizations separated by vast oceans and thousands of years arrive at the same breathtaking standard of accuracy? The styles are distinct, a testament to each culture's unique artistic vision. The Maya favored precisely carved limestone blocks for their pyramids, while the builders of Mycenae in ancient Greece used massive, rough-hewn boulders in what is known as Cyclopean masonry. Yet beneath these surface differences, a universal principle emerges. They all understood that the strength of a wall lies not in mortar, but in geometry. Each interlocking shape, each perfectly flat contact surface, distributes the immense weight and the energy of seismic shifts throughout the entire structure. It is a three-dimensional puzzle where every piece bears the load for its neighbor, creating a monolithic unity that is far stronger than the sum of its parts. Historians note that while these cultures left behind no blueprints for their methods, they left behind the evidence in the stone itself. The joint tightness, the selection of incredibly durable materials like granite and basalt, and the sheer longevity of these constructions all point to a profound and possibly shared understanding. Was this simply the inevitable result of human ingenuity solving similar problems, a convergent evolution of architectural thought? Or does it hint at something deeper, a lost thread of knowledge about the very nature of stone and stability, a forgotten school of craftsmanship that understood harmony between form and function on a level we are still struggling to comprehend? The global scale of this phenomenon forces us to look beyond isolated genius and consider a far more fascinating possibility. Walking through the old Inca capital of Cusco, the walls themselves seem to tell a story of resilience. Their zigzag patterns, built from countless irregular stones, form a monolithic puzzle that has shrugged off centuries of violent earthquakes. This is polygonal masonry in its most advanced form, a construction method where every block, with its unique many-sided shape, was painstakingly crafted to fit only its specific neighbors. The result is not a rigid wall, but a flexible, interconnected mass. When the ground shakes, these stones do not fight the energy, they dance with it. The entire structure shifts and settles, the stones moving as one, then settling back into place once the tremor passes. Modern structural engineers point to this design as a masterclass in seismic dissipation, a feature we strive to emulate with advanced materials and computer models today. The Incas achieved it with stone, patience, and an empirical genius passed down through generations. How did they do it without any written language to record their methods? The evidence suggests a process of relentless trial and error. Workers likely used harder hammerstones to pound the rough shapes from granite boulders. Then they would have painstakingly refined the contact surfaces, perhaps by rubbing one stone against another with a slurry of abrasive sand and water acting as a primitive cutting agent. A block would be trial-fitted, lifted by teams of laborers and any high spots marked. It would then be lowered, shaped again, and lifted once more, a cycle repeated until the fit was perfect. This was not a process of mathematical calculation, but of physical sensation, of sight and touch, until the stone literally locked into its destined place. The sheer human effort involved is almost incomprehensible, yet the proof of its success stands all around. This empirical mastery, this deep, intuitive understanding of material and form, invites a deeper question about the tools of the mind. What kind of knowledge, unspoken and unwritten, allowed them to see the final, perfect wall within the raw, unshaped mountain? Deep within the heart of the Great Pyramid, far from the eyes of the world, rest boxes of polished granite. These are not ornate tombs covered in hieroglyphs, but stark, unadorned sarcophagi found in subterranean chambers. Their significance lies not in decoration, but in their impossible geometry. The interior surfaces are flawlessly flat, with corners so sharp and precise they meet at perfect 90-degree angles, a feat that would challenge modern machinery. How could a culture using simple copper tools and abrasive sand achieve a level of flatness that resembles the work of a laser? The process itself is almost as mystifying as the result. To hollow out a solid block of granite, workers would have used tubular drills, likely made of copper, spun with a bow while a slurry of sand and water was fed into the cut. The sand, harder than the copper but softer than the granite, would slowly, grain by grain, abrade the stone. This method is understood in principle, but the execution defies belief. The precision of the drilling, the consistency of the cut, and the mirror-like finish left on the interior walls suggest a control and a patience that seems superhuman. Modern engineers who have studied these boxes note that to replicate their perfection today would require diamond-tipped cutting tools mounted on perfectly stable, computer-guided machines. The ancient Egyptians possessed none of this. They had copper saws, drills, and sand. The sheer amount of time and effort this would have consumed is staggering to contemplate. Each sarcophagus represents thousands of hours of relentless, focused labor. This was not a matter of brute force, but of sustained, delicate precision maintained over an incredible duration. The absence of any markings on these particular boxes only deepens the mystery. were they practice pieces for apprentices, honing their skills to an impossible standard? Or do they represent a purer form of knowledge, a functional mastery so complete it needed no symbolic explanation? The perfection of these granite boxes forces us to reconsider the very definition of a tool. Perhaps their greatest instrument was not copper or sand, but a profound, unwritten understanding of stone itself, a knowledge that allowed them to see the perfect form hidden within the rock and the disciplined will to set it free. The tools found in the archaeological record create a puzzle of their own. Inside a reconstructed ancient workshop, you would see copper chisels, stone hammers, and simple drills. These are the instruments officially credited with shaping history's most precise stonework, yet hold a soft copper chisel against a block of granite, one of the hardest stones on Earth, and the disconnect becomes obvious. Copper is too soft to cut granite directly. It would bend and blunt before making a significant mark. So how was it done? Archaeologists point to other tools in the kit. In Egypt, they found dolerite pounders, hard stone balls used to batter granite into a rough shape. In Mesopotamia, craftsmen experimented with stronger bronze alloys. These tools are effective for the initial, brutal work of splitting and roughing out a block, but they are inherently imprecise, incapable of creating the flawless, mirror-smooth surfaces and perfect 90-degree corners we find in places like the granite sarcophagi. This is the core of the tool mystery. The available tools explain the first 90% of the work, but they do not account for the final, breathtaking level of accuracy. This gap between the tools we have found and the quality we observe has led researchers to propose the use of perishable instruments. Perhaps they used wooden wedges, swollen with water, to split stone along precise lines. Maybe they employed stone polishing tools made from softer rocks, used with abrasive slurries of sand and water, to slowly grind surfaces to a perfect flatness over months or even years of painstaking labor. The true instrument may have been a technique, a forgotten process of rubbing and fitting that we have yet to fully comprehend. Experimental archaeologists have tried to replicate these methods. They use copper saws with sand and water to cut stone, and they can indeed make cuts, but the results are often slower, less precise, and leave a different surface finish than what is seen on ancient masterpieces. Their replications are convincing, but they are not perfect matches. Something is missing from our modern reconstructions, a subtle detail of technique or a specific type of tool that has left no trace in the soil. This suggests that the real tool was not just a physical object, but a profound, accumulated knowledge of material behavior, a sensory skill passed from master to apprentice. The true instrument may have been the human hand guided by an eye for perfection that we can scarcely measure, let alone replicate. A master builder in ancient times would have run a hand over a block of basalt, feeling its unyielding density. This stone, chosen for its ability to stand for millennia, presented an immense challenge before the first tool ever touched it. The difficulty of their task is measured by the Mohs scale of mineral hardness, a modern system that perfectly illustrates their ancient struggle. At one end lies limestone, a relatively soft stone that can be worked with copper tools. At the other extreme is granite, a rock so hard it is composed of interlocking crystals of quartz, feldspar, and mica. Quartz alone sits at a 7 on the Mohs scale, meaning it can easily scratch the copper of a chisel meant to shape it. This is the central paradox of ancient stonework, how cultures routinely tackled materials that were fundamentally harder than their available metal tools. The solution was not to overcome the stone with brute force, but to outthink it. Geologists point out that these early engineers possessed a deep, intuitive understanding of fracture mechanics. They learned to read the stone itself, identifying natural cleavage planes, hidden lines of weakness within the crystalline structure where the rock would most willingly split. Using simple tools like stone hammers and wooden wedges, they could encourage the granite to break along these predetermined paths, guiding the fracture with a precision that seems almost magical. There is also compelling evidence for the use of thermal shock, a method where a fire is built against the rock face and then rapidly cooled with water. The sudden expansion and contraction creates internal stresses, causing the stone to fracture in a controlled manner. Once a rough block was liberated from the quarry, the true artistry began. The shaping of these incredibly hard materials into their final, perfect forms relied on a different kind of knowledge, a patient, abrasive process. They used sand, a substance harder than copper but softer than granite, mixed with water to create a grinding slurry. With this simple mixture and tools made of even harder stone, they could slowly, meticulously, abrade the surface down to a flawless plane. The choice of material directly dictated the method. A soft limestone wall could be carved and adjusted with relative speed. A granite sarcophagus or a basalt statue demanded a different kind of commitment, a project that could span years where the final form emerged with glacial patience. This intimate relationship between the craftsman and his material suggests a school of knowledge built not on blueprints, but on tactile experience. How did they know when a surface was truly flat or an angle perfectly square without our modern instruments? The answer likely lies in a sensory skill we have largely lost, an ability to feel perfection with the hands and see it with an eye trained by generations of masters. This deep material wisdom leads us to an even more profound question about the nature of their work. Without a single measuring tape or laser level, ancient builders established perfect horizontals and verticals across vast construction sites. They achieved this using tools of elegant simplicity, tools that leveraged the fundamental laws of nature. To find a perfectly level line over long distances, they likely used water levels, a simple device of a trough or a length of hose filled with water. Because water always finds its own level, this gave them a constant, unchanging horizontal reference, a principle we still use in modern spirit levels. For creating perfect right angles, essential for squaring up foundations, they may have employed the 3-4-5 triangle rule. By marking a chord with knots at 3, 4, and 5 equal units, then stretching it into a triangle, they could guarantee a perfect 90-degree angle. This is a practical application of the Pythagorean theorem, a mathematical truth understood and used long before the philosopher gave it his name. The alignment of their structures reveals an even deeper layer of planning. Monuments across the world are precisely oriented to celestial events. A temple doorway might be positioned so the rising sun on the summer solstice illuminates the inner sanctuary, or a wall might run perfectly true north-south. This was accomplished not with magnetic compasses but with painstaking astronomical observation. A simple shadow pole, a vertical stake in the ground, could track the sun's path across the seasons. By marking the extreme points of the shadow at the solstices, they could establish a permanent, astronomically true axis for their entire construction. This fusion of earthly geometry and celestial cycles suggests their building was not just structural, but deeply symbolic, connecting their architecture to the cosmos itself. Evidence of this meticulous pre-planning is etched into the stone itself. At many ancient sites, archaeologists find stone trial models, small-scale mock-ups of the intended walls. They also discover incised guidelines, shallow grooves cut into bedrock to mark the exact placement of foundation stones. These are the ancient equivalent of an architect's blueprint. They reveal a systematic, methodical approach where the entire project was visualized and mapped out in advance. The master builders were not working haphazardly. They were executing a precise and sophisticated design. This combination of simple tools, natural principles, and advanced planning points to a form of knowledge that was both intuitive and profoundly mathematical. It was a geometry felt in the hands as much as it was calculated in the mind, a testament to a forgotten standard of accuracy that challenges our modern assumptions about the past. A master mason did not need complex machinery to design a perfect polygonal stone, only a compass and a straight edge. With these simple tools, he could generate a universe of geometric forms, laying out the intricate shapes that would lock together without mortar. This was not guesswork, it was applied mathematics. The evidence is etched into the stone itself, in the recurring proportions and sacred ratios that govern the world's most enduring structures. Historians point to the presence of constants like pi, the ratio of a circle's circumference to its diameter, encoded within the dimensions of the Great Pyramid. They note the use of the golden ratio, a proportion celebrated for its inherent sense of balance and beauty in the facades of Greek temples. These were not mere coincidences. They reflect a foundational belief that the universe itself was built upon mathematical principles, and that by echoing these principles in their architecture, they were creating a microcosm of cosmic order. This deep understanding of proportion did far more than please the eye. It was the very source of the structure's legendary strength. A wall built with harmonic proportions and precise geometric locking naturally distributes immense loads and seismic forces evenly across its entire surface. There are no weak points, no single block bearing a disproportionate share of the stress. The weight flows through the structure along predetermined geometric pathways, much like the forces flowing through the perfectly angled struts of a modern bridge. This mathematical foresight transformed a pile of heavy stones into a single, unified, and incredibly resilient entity. The choice of specific ratios often carried profound symbolic meaning, connecting the earthly construction to celestial cycles, philosophical ideals, or the human form itself. The application of geometry was therefore a dual act of engineering and reverence, a physical prayer built in stone. This sophisticated design philosophy makes you wonder if we have misunderstood their priorities entirely. Were they merely building walls, or were they constructing a permanent language, using mathematics and stone to speak across millennia about their understanding of a harmonious world? The perfect 90-degree angle inside a granite sarcophagus was not merely a technical achievement, it was a philosophical statement carved in stone. For cultures like the ancient Egyptians, the Maya, and the Inca, precision in construction was a bridge between the earthly and the divine. A perfectly flat surface mirrored the still waters of the primordial sea from which creation emerged. A corner meeting at a flawless right angle echoed the fundamental order of the cosmos, a stability they sought to replicate on Earth. This was not just building, it was a form of prayer, a physical act of devotion meant to please gods and immortalize the rulers who served as their intermediaries. When Maya artisans fitted limestone blocks for a pyramid with seams thinner than a leaf, they were not just constructing a platform, they were building a sacred mountain, an axis mundi that connected the human world to the realms of the gods above and below. The precision was the essential ingredient that made the structure ritually potent, transforming it from a pile of rock into a consecrated portal. Experts who study these cultures note that the drive for such exactness often came from a deep-seated belief in cosmic harmony. In this worldview, a sloppy, misaligned structure was more than just poor craftsmanship. It was an offense to the natural order, a potential source of cosmic imbalance that could invite misfortune or divine displeasure. This spiritual imperative provided the motivation for almost unimaginable effort. Why would a craftsman spend years polishing the interior of a granite box that would be sealed in darkness forever? The answer lies in understanding that the act itself held the meaning. The relentless pursuit of perfection was a demonstration of piety, a testament to the culture's dedication to its gods. This symbolic context transforms our view of the ancient works. We are not just looking at clever engineering solutions, but at the physical manifestation of a civilization's deepest beliefs about the universe and humanity's place within it. The stone itself becomes a language, and its perfect fit a syllable in a long-forgotten hymn to order and eternity. So how did this profound spiritual drive translate into the physical reality of a rising wall? The journey of a single stone from mountain to monument was a monumental undertaking in itself. It began in the quarry, where workers first had to persuade the earth to release its treasure. Using nothing but stone hammers and fire-hardened wooden wedges, they would begin the delicate process of extraction. They would hammer these wedges into a line of holes drilled along a natural fracture in the bedrock. Then, slowly, they would pour water over the wood. As the wedges swelled, they generated immense, even pressure, forcing the stone to crack cleanly along the intended line, freeing a multi-ton block from the living rock. This was not brute force, but a profound understanding of material science, a patient dialogue with the stone itself. Once liberated, the rough block faced a long and arduous journey. At sites like the Inca quarries, archaeologists have found meticulously prepared roads, stone-lined ramps that descend from the mountain, grooved by centuries of transported blocks. The stones were moved on wooden sledges, pulled by teams of laborers over rollers made of logs. On muddy terrain, they might even wet the path ahead of the sledge to reduce friction. The coordination required was immense, a symphony of human strength and simple physics guiding these giants for miles across the landscape. Arriving at the building site, the block was still only a rough approximation of its final form. The next stage was the shaping, a process that transformed a raw boulder into a precise, geometric piece of a vast puzzle. Workers used harder hammer stones to pound the surfaces, knocking off large protrusions and beginning to define the general shape. For the finer work, they turned to grinding. They would use handheld stones of quartz or basalt, rubbing them against the block with a slurry of sand and water. This abrasive paste, constantly replenished, acted like countless microscopic cutting teeth, slowly, relentlessly, wearing the stone down to a smoother plane. This was a dusty, grueling, and incredibly time-consuming task, but it was the only way to achieve the flatness required. The evidence for this process is etched into unfinished stones and abandoned blocks at sites worldwide. You can see the parallel grooves left by the grinding stones, the pockmarks from the hammering, and the incised guidelines that show where a cut was intended. These silent witnesses reveal a clear sequence, a methodical progression from rough to refined. The final and most critical stage was the fitting. This was not done on the ground but in place. Using ramps of earth and rubble, levers and ropes, teams would painstakingly raise the partially shaped block into its approximate position against its neighbors. Then the true artistry began. The masons would identify the high spots, the points of contact preventing a perfect seam. They would mark these spots, lower the block, and carefully abrade the identified areas before raising it again. This cycle of trial fitting, marking, and adjustment would be repeated over and over, sometimes for a single stone, until it settled into its place with that legendary paper-thin joint. The final exterior surface was often left rough until the entire wall was complete and perfectly locked, at which point it would be dressed smooth, erasing the evidence of the struggle and presenting a seamless face to the world. The sheer scale of this labor, repeated for thousands of stones, points to a society capable of extraordinary organization. It forces us to look past the stones themselves and ask who these people were, and what belief could possibly motivate such a sustained collective effort. Behind every perfect stone was a community of thousands. The silent walls we admire today were once a hive of human activity, a symphony of coordinated effort that required not just skill, but a society capable of immense organization. To achieve such precision, a clear and efficient hierarchy was essential. At the top were the master architects, the visionaries who understood the sacred geometry and the overall design. Beneath them were the master masons, the practical geniuses who could translate that vision into stone, directing teams of specialized craftsmen. Then came the quarrymen, the experts who knew how to read the rock and extract flawless blocks. The transporters who moved these multi-ton giants across the landscape. And finally, the stonecutters and finishers, the artisans whose patient hands and sharp eyes performed the final, exacting work of fitting. Each group had a distinct role, and the success of the entire project depended on their seamless collaboration. Historical records from Egypt, for instance, detail the existence of work crews with specific names, almost like modern corporations, suggesting a pride and identity tied to their craft. This was not a disorganized mob, but a highly structured workforce operating with a shared purpose. What could possibly motivate such a sustained and grueling collective effort? For many of these cultures, the primary motivation was a profound spiritual belief. Building a temple or a tomb was not just a construction job, it was a sacred duty, a direct service to the gods that ensured cosmic order and prosperity for the entire community. This divine purpose would have provided a powerful incentive for excellence. In other contexts, workers were compensated with food, shelter, and social status, forming a kind of professional class. While some projects undoubtedly involved forms of conscripted labor, the intricate skill and evident pride in the work suggest that many of the artisans were highly valued specialists. Their knowledge was not written in manuals but passed down through long apprenticeships. A young boy would learn by watching his father or a master, starting with simple tasks like mixing abrasive slurries or fetching tools, gradually progressing to rough shaping, and finally, after years of observation, being trusted to perform the final fitting of a stone. This system of hands-on learning ensured that the subtle, tactile secrets of the craft, the feel of a perfectly flat surface, the sound of a well-struck hammerstone, were transmitted from one generation to the next. This entire enterprise, from the quarry to the rising wall, was a testament to the human capacity for collaboration and innovation. It shows us that these ancient wonders were not built by magic or mystery, but by the disciplined, organized effort of countless individuals, each contributing their skill to a vision greater than themselves. How did this fragile chain of knowledge, passed from master to apprentice, manage to survive the rise and fall of empires? A master's knowledge lived in his hands, not in any written text. The art of cutting stone with impossible precision was a fragile flame, passed carefully from one generation to the next through a sacred chain of apprenticeship. A young learner would begin not with theory, but with observation, watching for years as his teacher selected the right hammerstone or mixed the perfect abrasive slurry. His first tasks were simple, perhaps fetching water or holding a measuring cord, all while absorbing the rhythms and rituals of the craft. He would progress to roughing out blocks, learning the feel of the stone's resistance, the sound of a clean fracture. Only after a lifetime of this gradual, immersive training would he be trusted to perform the final fitting of a critical stone. This was a knowledge of the body, a sensory skill built through relentless repetition and correction. The evidence of this training system is etched into discarded stones at ancient sites. Archaeologists frequently find trial pieces, rough blocks covered in practice cuts, and abandoned geometric shapes. These are the ancient equivalent of a student's notebook, showing the incremental steps of learning. Other sites reveal small, meticulously carved model stones, three-dimensional guides that may have served as a master's reference for his apprentices, a physical standard to emulate. The astonishing consistency in style and quality across centuries, visible in structures built generations apart, points to a tradition that was stable and self-correcting. This deep, accumulated wisdom was often protected within guilds or tightly knit familial lineages. A father would teach his sons, ensuring the secrets of the trade remained within the family, building a dynasty of masons whose very identity was intertwined with their skill. This system was incredibly effective for preserving knowledge across stable periods, but it was also profoundly vulnerable. The chain of transmission was only as strong as its weakest link. Historical records note that events like foreign invasions, widespread illness, or the collapse of a ruling dynasty could shatter these carefully built traditions in a single generation. If the master craftsmen were lost, the nuanced techniques they carried, the specific angle for a drill, the exact consistency of a polishing slurry, the tactile secret for testing a perfect seam, could vanish into the silence of history. This fragility forces a haunting question. If the very method of teaching was so susceptible to disruption, what subtle refinements, what entire chapters of practical stone lore might have been lost forever in the tumult of the past? The gap between the tools we have found and the perfection we observe may very well be the ghost of that forgotten classroom, the echo of a master's whispered secret that died with its last apprentice. The silence of the archaeological record can be deafening. When faced with stonework that defies simple explanation, it is only natural to wonder if we are missing a crucial piece of the puzzle, a technology that simply vanished. Could the ancient builders have possessed tools or techniques far more advanced than the simple chisels and hammers we attribute to them? Some researchers point to the sheer perfection of certain cuts and propose the use of sonic or vibrational devices, tools that could have resonated with the crystalline structure of the stone, causing it to separate along precise, predetermined lines with a clean, almost liquid flow. Others theorize about the use of powerful chemical agents, a paste derived from specific plants that might have temporarily softened the surface of the granite, allowing artisans to mold it like clay before it hardened back to its original, diamond-like strength. The most sweeping of these alternative theories suggests the handiwork of a much older, sophisticated civilization, a global culture whose advanced knowledge was later inherited by the Egyptians, the Inca, and others, explaining the eerie similarities in their precision. While these ideas capture the imagination, they face a significant challenge: a complete lack of physical evidence. No ancient sonic cutters have been unearthed. No recipes for rock-softening plants have been found in any hieroglyphic text or artifact. The mainstream archaeological view remains that the available tools, combined with immense skill and patience, are sufficient to explain the phenomena. The true value of these alternative theories is not in their proof, but in the questions they force us to ask. They push us to look more carefully at the evidence we do have and to remain humble in the face of what we do not know. They remind us that history is not a closed book, but a story still being deciphered. This willingness to question, to look beyond the conventional, is what ultimately drives the next phase of the quest, as modern science turns its most sophisticated instruments toward the stone itself. A laser scanner glides silently over the surface of an ancient Inca wall, capturing millions of data points in a single pass. This is not a treasure hunt, but a digital autopsy, an attempt to see what human eyes cannot. Modern archaeologists are now employing tools like 3D laser scanning and photogrammetry to create hyper-accurate maps of these stone surfaces. These digital models can be rotated, zoomed, and analyzed to reveal subtle variations in flatness and the microscopic topography of every cut. They can measure the legendary tightness of the joints down to a fraction of a millimeter, confirming the almost unbelievable tolerances that have been described for centuries. But the technology goes far beyond simple measurement. By analyzing the shadows and contours in these digital models, researchers can identify the unique signatures left by specific tools. They can distinguish the parallel striations of a saw cut from the pitted surface left by a pounding stone, effectively reading the story of the stone's creation from its final form. In Egypt, material analysis has taken this detective work even further. By taking microscopic samples from the interior of drill holes in granite boxes, scientists have identified the precise types of abrasive sand used, like emery or quartz, confirming the use of specific, locally sourced materials in the cutting slurry. This technological scrutiny is not just about confirming what we already suspected. It has also been instrumental in debunking long-held myths. For decades, some theorists pointed to certain stone cuts as evidence of advanced lost machinery. Yet when these same cuts were subjected to digital analysis, the scan data revealed the faint, telltale marks of repetitive manual labor, the very human signature of a copper saw pulled back and forth by hand countless times. Computer simulations then take this physical data a step further, modeling how these precisely fitted walls behave under immense stress. Engineers can input the exact dimensions and weights of the stones to watch how forces flow through the geometric puzzle during an earthquake, visually demonstrating the genius of the polygonal design. These high-tech methods are peeling back the layers of time, transforming speculation into data and legend into engineering principle. The next logical step in this quest is to take this digital understanding and put it to the ultimate test, to see if modern hands, guided by ancient clues, can actually recreate the impossible. An experimental archaeologist stands before a freshly quarried block of granite, armed with a copper saw and a bucket of sand. This is the moment of truth, a modern attempt to walk in the footsteps of ancient masters. For months, the team works, dragging the soft metal blade back and forth, constantly feeding the abrasive sand and water slurry into the cut. Progress is achingly slow, the grating sound a constant reminder of the immense task. They can indeed cut the granite, proving the method is fundamentally sound. Yet, when their finished block is measured against an ancient counterpart, the difference is stark. Their cut is wavier, the surface noticeably rougher, and the entire process took far longer than most historical timelines would comfortably allow. This gap between possible and perfect is where the real mystery lies. In another experiment, skilled stonemasons try to replicate the polygonal masonry of the Incas using only hammerstones. They can rough out the shapes, but achieving that legendary, tight fit becomes a frustrating exercise. Their joints remain visible, their seams measurable with a common ruler, a far cry from the paper-thin perfection that defines the ancient walls. These are not failures but profound lessons. They reveal that simply having the right tools is not enough. The missing ingredient seems to be a deep, embodied skill, a nuanced understanding of how much pressure to apply, the exact grain size of the ideal abrasive sand, and the precise rocking motion needed to polish a surface to a flawless plane, not just a smooth one. What takes a modern team months of deliberate effort may have been accomplished with a fluid efficiency by an ancient artisan who had performed the same motions since childhood. The experiments suggest we are missing the rhythm of the craft, the accumulated tricks of the trade that transformed a theoretical process into a masterwork. This repeated shortfall forces a humbling admission. Our modern minds, accustomed to power and speed, may lack the patience and the subtle tactile intelligence that was second nature to those builders. We are trying to copy the notes without understanding the music. The enduring legacy of their work is not just in the stones they left behind, but in the silent challenge they issued to the future. A visitor from a distant land, standing before the cyclopean walls of Mycenae or the soaring pyramids of Giza, would have felt more than just admiration. They would have felt an overwhelming sense of power. This impeccable stonework was a civilization's ultimate declaration of strength, a message carved in granite that echoed across generations. The cultural impact of such precision was profound, shaping every facet of society from its spiritual core to its economic pulse. The ability to command stone with such authority was not merely an architectural feat, it was a potent political tool. A ruler who could marshal the labor and skill to build an eternal temple or an impregnable fortress was demonstrating a godlike control over both nature and people. This visible proof of organization and resources served as a powerful deterrent to potential enemies. Who would dare attack a kingdom capable of such monumental works? Simultaneously, these structures acted as magnificent beacons, drawing pilgrims, scholars, and merchants from across the known world. This influx of visitors fueled local economies, creating markets, supporting artisans, and bringing wealth and prestige to the center of power. The great temple complexes of the Maya, for instance, became thriving hubs of trade and ceremony, their precision a testament to the divine favor bestowed upon the ruling class. This divine connection was the bedrock of their spiritual authority. When a society could build a mountain of stone that perfectly aligned with the solstice sun, it proved a special relationship with the gods themselves. The precision was the evidence of that covenant, reinforcing a social hierarchy where the elite were the essential intermediaries between the people and the cosmos. This created a cycle of reinforcement. The spiritual belief motivated the immense labor, and the resulting architectural marvel, in turn, solidified that very belief for every new generation. The structures themselves became the ultimate symbols of cultural identity and resilience. Long after the voices of the builders fell silent, their stones continued to speak. The walls of Sacsayhuaman did not just survive earthquakes, they survived the collapse of the Inca Empire itself, standing as a permanent reminder of a people's genius. These legacies in stone challenge our modern notions of value and time. They force us to ask what we are building today that will whisper our story to the world 1,000 years from now. This reflection on their lasting impact naturally turns our focus to the fundamental engineering principles that granted these stones their incredible endurance. That legendary tight fit is more than just a testament to patience. It is a masterclass in structural engineering. A wall built with such precision behaves not as a collection of individual blocks, but as a single, unified mass. The secret lies in how it manages force. In a conventional wall held together with mortar, the mortar itself is often the weakest link. It can crumble under its own weight over centuries or crack apart during an earthquake, causing the entire structure to fail. But in a dry stone wall with perfectly fitted joints, there are no weak links. The immense weight of the stones is distributed evenly across every single point of contact. Each stone, locked in a three-dimensional embrace with its neighbors, shares the burden. This creates a state of equilibrium where the downward force of gravity is transformed into a stabilizing pressure that pushes inward, holding the entire assembly together. The sheer mass of the stones, combined with the immense friction generated by their perfectly flat surfaces pressing together, makes the wall incredibly resistant to sliding or toppling. Experts point to the Cyclopean walls of Mycenae in Greece as a prime example. These colossal boulders, fitted with such accuracy, have stood for millennia, their stability derived entirely from their geometry and weight, defying time and tremors. This principle of interlocking strength finds its ultimate expression in the zigzag walls of the Inca. When an earthquake strikes, a rigid building fights the seismic waves, often shattering in the process. But the Inca walls are designed to dance. The complex polygonal joints allow for tiny, almost imperceptible movements. The entire structure flexes and shifts as a single, flexible entity, absorbing and dissipating the destructive energy. When the shaking stops, the stones settle back into their original, locked positions. This is not a mystical property. It is simple, brilliant physics understood through generations of observation and experimentation. The ancient builders were empirical engineers, learning through trial and error how to make stone defy its own nature. This deep, intuitive grasp of physical forces raises a compelling question. Did their understanding of earthly stability also extend to the heavens above, guiding them to align their creations with the sun, moon, and stars? A stone circle silhouetted against the dawn sky is more than a monument. It is a celestial clock. That first ray of sunlight piercing a specific doorway on the spring equinox was not a happy accident. It was the culmination of generations of patient observation. Across the ancient world, the same impulse emerged to capture the rhythms of the cosmos in unyielding stone. At Machu Picchu, the Intihuatana stone, a precisely carved granite pillar, functioned as an astronomical instrument. Its angles and shadows marked the exact dates of the solstices, allowing Inca priests to track the sun's journey with stunning accuracy. Far away on the Salisbury Plain, the massive sarsen stones of Stonehenge are aligned to frame the summer solstice sunrise, an event that still draws thousands to witness its ancient precision. These alignments were not merely decorative, they were essential. They created a calendar etched into the landscape, dictating the optimal times for planting and harvest, for religious ceremonies, and for reaffirming the cosmic order. This required a sophisticated merger of skills. The same artisans who could shape a granite block to a perfect flatness also had to understand the slow, grand dance of the heavens. They used simple yet profoundly effective tools for this celestial mapping. A shadow cast by a solitary pole, observed over years, could chart the sun's shifting path. The rising point of a key star over a distant mountain, noted season after season, became a fixed astronomical marker. The true challenge was then to translate these observed points on the horizon into the permanent, physical alignment of multi-ton stones. This was a feat of engineering as much as astronomy. The foundation of a temple had to be laid with perfect levelness, its walls built with flawless verticality, and its key apertures oriented to a precise azimuth, all to ensure that the celestial event would perform its annual drama as intended. The result was a living architecture, a structure that interacted directly with the sun, moon, and stars. This integration reveals a worldview where the earthly and the heavenly were inseparable. The precision of their stonework was not just for structural integrity, but for cosmic harmony. It prompts a profound question about the very purpose of their craft, moving us from pure engineering to consider the deeper aesthetic and spiritual vision that guided the master's hand. The seamless joints of an ancient wall do more than ensure its strength. They create a canvas for the sun. As light travels across these perfectly flat surfaces, it casts sharp, clean shadows that emphasize the geometric patterns and give the stone a living, breathing presence. This was not an accident. For many ancient cultures, the pursuit of technical precision was inextricably linked to a deep desire for beauty. The aesthetic goal was visual harmony, an ideal where every line and surface contributed to a sense of sublime order. Art historians note that in societies from India to Egypt, beauty was not a secondary consideration. It was a fundamental driver of the entire building process. The flawless fit of the stones was what allowed for the creation of vast, unbroken surfaces that could then be adorned or left in a state of minimalist perfection. Look at the elaborate carvings covering the temples of Khajuraho in India. Every celestial figure and intricate floral motif is rendered with breathtaking detail, a feat only possible because the underlying stone blocks were first joined with near-invisible seams, creating a stable, monolithic canvas for the artist. The precision came first, the art followed. Conversely, consider the stark elegance of an Egyptian obelisk. Its power derives from its flawless geometry, the razor-sharp edges and mirror-smooth faces that catch the desert light. Here, the technical precision is the artistic expression. The stone itself, cut and placed with impossible accuracy, becomes the object of awe. This fusion of form and function points to a shared philosophical understanding. These civilizations saw the universe as a place of inherent order and balance, and their architecture was a deliberate attempt to reflect that cosmic harmony on Earth. A sloppy joint or a wavering line was not just poor craftsmanship, it was a philosophical misstep, a disruption of the natural balance they sought to emulate. The relentless drive for accuracy was therefore a spiritual and artistic imperative as much as an engineering one. It was about creating a legacy in stone that was not only eternal but also beautiful, a permanent testament to a culture's highest ideals of what the world could and should be. A temple was far more than a building, it was a model of the entire cosmos. This profound philosophical drive transformed stonework from a craft into a sacred language, where every perfectly cut block and every seamless joint articulated a belief in a harmonious universe. In the jungles of Cambodia, the Temple of Angkor Wat was constructed as an earthly representation of Mount Meru, the mythical center of the Hindu and Buddhist cosmos. Its precise concentric galleries and towering peaks were not just an architectural choice, they were a cosmological map. The accuracy of its construction was what made it symbolically potent, allowing it to function as a true axis connecting the human and divine realms. Similarly, Maya pyramids in Mesoamerica were often conceived as sacred mountains, their steep stairways symbolizing the path to the heavens. For the builders, a slight misalignment in the stones was not a simple engineering flaw. It was a tear in the symbolic fabric of their world, a risk of severing the crucial link between their community and the gods who govern the rains, the harvest, and the very cycle of life. This spiritual imperative provided the ultimate motivation for the relentless pursuit of perfection. The arduous labor of polishing granite for years was not a burden, but an act of devotion, a physical prayer offered stone by stone. When we look at these structures today, we are not merely seeing clever construction, we are witnessing the physical manifestation of an entire civilization's worldview. The silent stones speak of a universe governed by order, balance, and meaning, and of humanity's role as a conscious participant in that grand design. This shared desire to encode cosmic truth into stone raises a compelling question. How did such similar philosophies emerge in cultures separated by vast oceans and impossible distances? The soaring arches of a Gothic cathedral and the sloping stone base of a Japanese castle represent two different worlds of precision. In Europe, medieval masons pursued a vision of heavenly aspiration, using complex geometry to carve the precise keystones and ribs that would lock together to form vast, vaulted ceilings. Their precision was one of calculation and line, creating a skeletal stone framework that allowed walls to be filled with light and stained glass. Meanwhile, on the other side of the world, Japanese builders faced a constant and immediate threat, the tremors of the earth. Their precision was one of mass and stability. They constructed immense castle foundations using a technique called burdock piling, where rough, uncut boulders were carefully selected and fitted together with smaller stones hammered into the gaps. The result was not a smooth wall, but an interlocking, flexible base that could sway and absorb seismic energy without collapsing. Both traditions achieved legendary durability, yet their methods were a direct reflection of their environment and beliefs. European masons, working with abundant limestone and sandstone, could focus on intricate shapes and open, luminous spaces. Japanese builders, often using the hard, volcanic rock of their islands, prioritized a low, formidable center of gravity. Experts note that these differences reveal a profound truth about precision. It is not a single, universal standard, but a language spoken with a unique accent in every culture. The goal was the same, to build something that would last, but the path was shaped by the available stone, the dominant threats, and the spiritual ideals of the age. This incredible diversity of solutions only makes the core mystery more compelling. If cultures could arrive at such different yet equally effective forms of mastery using only hand tools and empirical knowledge, what other secrets of stone did they discover that we have yet to uncover? These perfectly shaped spheres of stone, scattered across the Diquis Delta of Costa Rica, present a problem that geometry alone cannot solve. Ranging from the size of a melon to the weight of a small car, their surfaces are so smoothly curved and their shapes so ideally spherical that their creation defies the known toolkits of the cultures that made them. How does a society without written records of their methods sculpt granite into near-perfect orbs? The leading theory suggests a process of meticulous pecking and grinding with harder stones, followed by polishing with sand. Yet, the sheer consistency and perfection of the largest spheres leave room for doubt, hinting at a lost technique for controlling form that we have yet to rediscover. An ocean away, the vitrified stone forts of Scotland present an even more dramatic puzzle. Here, the very rock of the ancient walls appears to have been melted and fused together, as if by immense heat. The stone is glazed and bubbled, literally vitrified into a glass-like substance. Archaeologists have long debated the cause. Was it accidental, the result of a catastrophic fire that raged hot enough to melt granite? Or was it intentional, a forgotten method of construction meant to strengthen the ramparts by turning them into a single, solid mass? Experiments have shown that sustained, intense heat can achieve this effect, but replicating it on the scale of an entire fort wall and explaining why ancient builders would go to such extreme lengths remains one of the field's most heated debates. Then there is the question of movement. At the Lebanese site of Baalbek, a stone known as the Hajar al-Hibla, or Stone of the Pregnant Woman, lies in a quarry. It weighs an estimated 1,200 tons. Nearby rests an even larger block, weighing over 1,650 tons. How were these megaliths, the largest ever cut by human hands, intended to be transported even a short distance? The conventional explanation of log rollers and rope teams seems to strain under such incomprehensible weight, pushing our understanding of ancient logistics to its absolute limit. Further mysteries lie in the smallest of details. In Egypt and South America, we find examples of deep, narrow holes drilled into the hardest stones like granite and basalt. The bore is perfectly cylindrical with consistent, parallel grooves spiraling down the interior. While the use of a tubular drill with an abrasive slurry is understood, the precision and depth of these holes, sometimes extending the length of a human arm, suggest a level of stability and sustained pressure that challenges our reconstructions of ancient technology. These are not isolated quirks, but a pattern of puzzles that refuse to yield simple answers. They stand as permanent reminders that our historical narratives are still incomplete. The enduring nature of these mysteries is not a failure of modern science, but a gift. It forces engineers and archaeologists to look beyond conventional thinking, to question long-held assumptions, and to consider that the ancient masters of stone may have possessed a different kind of knowledge, one rooted in a deep, intuitive partnership with their materials. What lessons in sustainability, in material science, and in patient, precise craftsmanship might we learn if we could finally decipher their silent, stone-coded language? That same principle of interlocking geometry is now finding its way into modern blueprints. In earthquake-prone regions from Japan to California, contemporary engineers are actively studying the polygonal masonry of the Inca. They are not copying the stones, but the underlying concept, designing buildings that can sway and flex with seismic forces rather than resist them rigidly. This ancient idea of passive stability, where a structure dissipates energy through its own interconnected design, is a powerful alternative to our complex and expensive systems of active damping. It is a lesson in resilience learned not from computer models, but from walls that have endured for 1,000 years. Another profound lesson is material efficiency. Ancient builders had no room for waste. Every piece of stone was carefully selected and shaped to serve a specific structural purpose. This stands in stark contrast to much of modern construction, where materials are often over-engineered and surplus is common. Experts point to this ancient approach as a precursor to today's sustainable design principles, where minimizing waste and maximizing the inherent strength of materials is a primary goal. The very longevity of these structures is a masterclass in sustainable building, proving that durability is the ultimate form of green architecture. we are also rediscovering the power of load distribution through geometry. The way a perfectly fitted Inca wall turns the weight of each stone into a stabilizing force is being revisited in cutting-edge projects. Architects are experimenting with complex three-dimensional puzzles for facades and foundations, using digital fabrication to create interlocking components that require no mortar and possess incredible inherent strength. These are not nostalgic recreations, they are the next evolution of building science, informed by empirical wisdom that has been tested by the ultimate judge, time itself. Applying this ancient knowledge to our current challenges, from resource scarcity to climate resilience, reveals a timeless truth about good design. It shows that the most elegant solutions are often rooted in a deep understanding of natural forces and a respectful, efficient use of materials. The silent stones of the past are becoming unexpected teachers for a more sustainable future. A gentle laser scan now charts the slow decay of a wall that has stood for 1,000 years. The very precision that ensured its longevity is now threatened by the world it has endured. Modern preservationists face a delicate battle against invisible enemies, moisture seeping into microscopic seams and freezing, the slow, inexorable pressure of tree roots, and the cumulative wear from the footsteps of countless admirers. Their tools are as sophisticated as their mission is urgent, using ground-penetrating radar to see inside the walls without touching them, and drones to map erosion patterns across entire sites. The goal is never to restore these structures to a false sense of newness, but to stabilize them, to halt the progress of time just long enough for their story to continue. International collaborations, like those led by UNESCO, bring together engineers, geologists, and historians to share knowledge and resources. They document every stone with 3D modeling, creating a digital archive that will survive long after the originals have further weathered. Repairs are made with a profound respect for the original craftsmanship, using stones from the same quarries and traditional mortars that are chemically compatible, ensuring new work does not inadvertently damage the old. This global effort is a testament to the universal value we now place on these achievements. It forces us to confront a difficult balance, allowing people to witness these marvels firsthand while protecting them from the damage that visitation inevitably causes. Solutions range from simple walkways that redirect foot traffic to advanced climate control systems within sealed tombs. Every preserved stone is a bridge, a direct connection to the minds and hands of the ancient builders. By safeguarding their work, we honor not just the stones themselves, but the human ingenuity they represent, a legacy of patience and perfection that asks us what we, in our own time, will choose to build and protect for the generations yet to come. That silent connection you feel standing before a wall fitted by hands centuries gone is more than just awe. It is a direct line to the core of human potential. These stones are a testament to a truth we often forget in our age of instant results, that profound achievement is born not from magic, but from a powerful combination of patience, ingenuity, and a shared vision that spans generations. The builders did not possess tools that made the work easy. They possessed a mindset that made the impossible achievable. They looked at a mountain of unshaped granite and saw within it a perfect wall, a legacy waiting to be revealed, one careful tap, one patient grind at a time. This was problem-solving at its most fundamental and most brilliant, a dialogue with the material itself. Every perfectly flat surface, every seamless joint is a solved equation, an answer to a physical challenge met with observation, experimentation, and relentless perseverance. They teach us that collaboration is the true engine of greatness. No single person could have moved that block or conceived that geometric puzzle. It required the architect's vision, the quarryman's strength, the mason's sensitive touch, all working in concert toward a goal greater than any individual. The most inspiring lesson may be their understanding of time. They invested years, even decades, in projects they knew they would never see completed, building for their grandchildren's grandchildren. This long-term thinking, this faith in the future, is perhaps the most powerful legacy they left behind. It asks us a simple, profound question about our own endeavors. What are we building today, not with stone, but with our ideas, our communities, and our care, that will whisper our story of dedication to the world 1,000 years from now? The echoes of ancient hammers have long since faded, but the questions they raised still resonate. From the polygonal walls of the Andes to the granite sarcophagi of Egypt, we have walked through a landscape of impossible precision, a global phenomenon of craftsmanship that defies simple explanation. We have uncovered the empirical skills of the masons, the simple yet profound tools they wielded, and the powerful cultural drives, both spiritual and political, that fueled such relentless dedication. These were not separate endeavors, but threads woven into a single, magnificent tapestry of human achievement. The true secret was not a single lost technology, but a complete fusion of art, science, and belief, a mindset that saw perfection as a sacred duty and patience as the ultimate tool. This universal pursuit reveals something fundamental about our shared history, an inherent capability for greatness that emerges when a community is united by a vision greater than itself. These silent stones are more than just monuments. They are a timeless lesson in resilience, collaboration, and long-term thinking. They challenge us to look at our own modern world, at our own fleeting projects and immediate gratifications, and to ask what we are building with our hands and our hearts that will truly endure. If this journey into the depths of history has sparked your curiosity, we would love to hear your thoughts in the comments below. Share which mystery captivated you the most. And if you are ready for more deep dives into the greatest enigmas of our past, subscribe to continue exploring with us. Together, we keep the wonder of human ingenuity alive for the future.